Here's a walkthrough of paper 1, AQA A-level Chemistry, Inorganic and Physical Chemistry. This is the June 2017 paper. Okay. So the question about silver iodide: define the enthalpy of lattice formation. Well, it's the enthalpy change occurring when 1 mole of an ionic compound formed from its gaseous ions. And it's pretty exothermic. Lattice enthalpy of dissociation is the opposite of that. Okay, it's not asking, that's asking formation there. Okay, so some enthalpy change data is shown below. So it's giving us, right, this is called a delta H solution. When you dissolve 1 mole of the ionic solid in water. This is the hydration energy of the silver ion, and this is the hydration energy of the iodide ion. So when you get the gaseous ion, you put it into water, and it's always pretty exothermic. You can see negative because you're forming an interaction between, well, in the case of the silver ion, the delta negative water molecule, the delta negative oxygen in the water molecule. In the case of the iodide ion, the delta positive hydrogens of the water molecule. Okay, so we need to work out lattice enthalpy. So we need to use this Hess's law cycle. So we've got Ag solid going to Ag aqueous and iodide. That's what we want to find out. Sorry, that's what they tell us there. That's the enthalpy of solution. If we put down here the gaseous ions, okay, so here we've got the ions in aqueous solution. Here we're going to have the ions as gases. Ag gas and I minus gas. Okay, so we know the number of this one. This, they tell us that's plus 112. It's pretty endothermic, and that's why silver iodide incidentally won't dissolve. It's insoluble because that is too endothermic. Here we're getting the gaseous ions. When we put them in aqueous solution, we're hydrating them. So that means we've got to add 464 for the minus 464 for the silver, hydration of silver ion, and minus 293 for the hydration of the iodide ion. If we add that together, we get a total of minus 757 there. Now this one, we need to find the lattice enthalpy of formation. So I'm going to put the arrow going that way because that is lattice enthalpy of formation. That red one, that's what we've got to find out. So we can see there the lattice enthalpy of formation. Right, we're going with right, so we want to go from there to there. So we are going, sorry. First of all, we're going up there. We're going with the arrow there. So that's minus 757. And then we're going there, we're going against the arrow. So we change the sign there to minus 112. And that gives us minus 869 kilojoules per mole as our final answer. Okay, so that little cycle, you have to remember that. Hydration energy, so that's the cycle which involves delta H hydration energies, lattice enthalpies, and the enthalpy of solution, that little triangle. Okay. Okay, 1.3. Calculation of the enthalpy of lattice enthalpy of silver iodide based on perfect ionic model gives us smaller numerical values than the value calculated. Explain this difference, right? So when you get poor agreement between the Born-Haber lattice enthalpy and the theoretical value based on the ionic model, it means the ions are not spherical, because that's an assumption when you do the calculation, the ions are spherical. So I would say there that means that the compound AgI, in this case, has partial covalent character. Right, that's going to get you 1 mark for that. Then I think for the other mark, you have to say why is it the theoretical smaller? It's not as exothermic as the real value. So you need to say that the interactions in the real solid are stronger than in the theoretical solid, i.e. with perfectly spherical ions. Right, you need to have that bit in red there to explain the small and numerical. You can't just say they're different because there's partial covalent character. It's only 2 marks. You don't need to go into the explanation there that it's the Ag plus ion which polarizes the iodide ion. You don't need to go into that explanation for just 2 marks. Okay, identify a reagent, so a bit of inorganic chemistry because this is physical inorganic. That can be used to indicate the presence of iodide ions, I-. Well, that's your straightforward recall of your knowledge. You would, you add silver nitrate solution. So you've got to still say silver nitrate solution. You can't say silver ions. Whenever it says a reagent, you've got to give the actual name of a chemical. You can't say like, acid, you've got to say H2SO4, you can't say H plus ions. You've got to say silver nitrate in aqueous solution, and the observation is a yellow precipitate would form. Right. This is a longest question on acids and acid equilibrium. Okay, so they give you a value, they give you the equation there for the dissociation constant of ethanoic acid, which is a weak acid, obviously, and they give the value of Ka, and then it says, right, you've got a buffer solution. Right, now they give you the pH of the buffer solution. They give you the concentration of the ethanoate ions, let's call that A-, and we've got to calculate the concentration of the ethanoic acid, let's call that HA. Now, normally when I do a buffer calculation, so that's going to be A- concentration H plus over HA, I normally say, like, let's rearrange that to give us H plus, and H plus is equal to Ka HA over A-. That's good practice for a normal buffer. We don't really need to do that in this case because we just need to find the concentration of A-. So let's make A- the subject of that equation then. So we get A- is equal to Ka HA. Sorry, we need to find HA, don't we? Not A-. Rearrange to get HA. HA is A- times H plus over Ka. Now, don't fall into the trap of thinking that A- concentration is equal to H plus and call that H plus squared. That's not true in this case. That's only true when you've got a weak acid that you haven't added some sodium ethanol, some of the, we've added a load of A-, in this case we have. H plus is not going to be equal to that. So don't fall into that trap. You can't use that this time. Okay, so HA, let's put the numbers in. Right, H plus concentration is equal to 10 to the power of minus pH, which is equal to 10 to the power of minus 3.87 here. Put that into your calculator, you get 1.349 times 10 to the minus 4 moles per decimeter cube. That's the concentration of H plus. Let's put the numbers into that. HA concentration then is going to be equal to A-. We've got 0.136 multiplied by 1.349 times 10 to the minus 4. That's our H plus concentration. Divided by HA, 1.74 times 10 to the minus 5. do that, you get a value of 1.054 moles per decimeter cubed. So 3 significant figures, let's call that 1.054. Quick common sense check there. Well, the concentration of HA and A minus are usually fairly similar to each other, and that's okay because, you know, what do we get? The concentration of HA was 0.136, so it's in the same order of magnitude there. So it's, and it is the right answer, but it's worth giving it a common sense check. Okay, now this question is harder. Right, in a different buffer solution, the concentration, I'm going to make myself some room here as well. Right, in a different buffer solution, the concentration of ethanoic acid, so we've got the HA concentration is equal to that, and the ethanoate ions was equal to that. We've got a volume of 500 centimeters cubed, and the which is makes things a little bit difficult because quite often they say the volume is 1 dm cubed to make life easy for you, and they haven't done that here. And then we add a certain number of moles of sodium hydroxide. Okay, so let's do that. Right, so I said whenever we do a buffer calculation, I always like to rearrange the Ka expression to give us H plus as the subject, so we get Ka HA over A minus. Right, now what I'm going to do here is I'm going to work out, I'm not going to use the concentration, I'm going to work out the moles of HA. So moles of HA is equal to the conc times volume. All right, the reason why we're going to do that, we're going to have to find out the moles, because the concentration is going to be no good because we need to know how many moles of the HA react with the sodium hydroxide. So the moles of HA is going to go down, the moles of A minus is going to go up. So we need to work out how many moles of HA we've actually got. Conc times volume, so we've got 0.26 is the concentration of the HA. The volume is 0.5 dm cubed. That's 0.13 moles. Let's do the same for the moles of A minus. Conc times vol. The concentration is 0.121 multiplied by 0.5, which is equal to 0.0605. Okay, now this is where we need to work out the number of moles in this next step. Because what we're going to do here is we're going to write a little equation. We're going to have HA is going to react with OH minus to give us A minus and water. Okay, I'm going to write down the start moles of HA. So we're going to start off with 0.13. We worked out from there. Start moles of A minus 0.605. It's 0.0605, sorry. I don't care about the water, so I'm just going to leave that. The moles of OH minus, they tell us here, is 7 times 10 to the minus 3. So that's 0.007. So let's now do final moles. Right, so the HA is going to go down by that much. So that's 0.13 minus 0.007. So that's going to give us 0.123. And the A minus is going to go up by 0.007. So that's going to go to 0.0765. 675, sorry. Okay. Again, we don't care about that. We're going to presume all the OH minus is gone. Now, are we ready to put that into this equation? We are not, because that's square brackets. That means concentration, not moles. So, right, we do know, well, we sort of know what the final volume is. It's 500 centimeters cubed, but I think it's going to be a tiny, tiny bit more than that because you've added some sodium hydroxide. That's going to increase the volume a little bit. We don't need to know what the real volume is because let's call the volume V. Okay, let's call the volume V, and we'll see the V's will cancel out. So final concentration is 0.123 over V, and 0.0675 over V. Let's put our numbers into this equation here. So we've got H plus is equal to Ka, which they told us 1.74 times 10 to the minus 5, multiplied by concentration of Ha, 0.123 over V, divided by the concentration of A minus, 0.0675 over V. What's going to happen to those V's? They're both in the same volume, so they cancel out. And in a buffer solution, those V's will always cancel out because obviously they've got to be in the same volume because they're in the same solution. Okay, so work out that number and you get H plus is equal to, put in your calculator, you will get H plus is equal to 3.17 times 10 to the minus 5 moles per decimeter cubed. Take minus logs to get the pH. You get 4.498. Give it to 2 dP, 4.50 is the pH. That's the answer there. Okay, so I would always use that method when you're working out buffers like this, is to use, you get the concentrations, call the volume V, the V's will all cancel out, and most importantly, don't confuse moles with concentrations. Okay. Right, which is the right expression for the Kw? Well, normally we write down Kw like that, don't we? Yeah. So that is the right one. We don't include the it's for this equation, isn't it? H2O goes to H plus OH minus. Really, that is H3O plus. You can have that as H3O plus in the expression if you want. So we'd not forget, if we wrote Kc for that expression, we'd normally write, this one here, wouldn't we? But we don't include the value of the concentration of H2O because it's much higher than the others, so it's more or less constant. So that is the expression that is the right answer, that one there. Sorry, it's not the right one at all. This one, C, is the right one. Yeah. Okay, so we're going to use that expression in the next part of the question. Calculate the pH of pure water at 10 degrees C. Now, at 10 degrees C, the value of Kw is not 1 times 10 to the minus 14. It's smaller. It's that value there. So we need to use that value of Kw. So, well, the way we do this is we're going to say that, right, Kw is equal to H plus conc times by OH minus conc. And when it's neutral in pure water, nothing else has been added, H plus concentration is equal to OH minus concentration. Substitute that value into there, we get Kw is equal to H plus squared. So H plus concentration is equal to the square root of Kw, the square root of 2.93 times 10 to the minus 15. That gives us 5.41 times 10 to the minus 8. Log it to get the answer. We get pH minus log it 7.26. Right. That is the answer. Now, the next part of the question is very common. Why is this not alkaline? Well, look, you've got a pH of greater than 7.26. And you're sort of being brainwashed since the ages of 10 to think anything above 7, pH 7, is alkaline. Well, it's not always. And you've been brainwashed to think neutral is pH 7. It's not always. Neutral is, strictly speaking, H plus concentration is equal to OH minus concentration. And it so happens that 298 Kelvin, that is pH 7. But you go away from that temperature, it's not the case. So all you have to say here is because basically H plus concentration is equal to OH minus concentration, it's not alkaline, even though it's more than 7. Okay, calculate the pH of a solution of calcium hydroxide. Right, quite sneakily, they don't give the formula of calcium hydroxide here, but of course it's in group 2, and that's on this topic, on this paper as well, isn't it? Group 7, group 2 in organic chemistry. It's that. So you have to remember, if you've got a concentration of that for calcium hydroxide, the OH minus concentration is not equal to 0.132, it's double that, because you get 2 moles of OH for one. Yeah, so it's going to be 0.0262. Right, we need to calculate the a hydrogen ion concentration, so we're going to use Kw is equal to H plus multiplied by OH minus. So H plus is equal to Kw over OH minus concentration. So that's going to be 2.93. They give us the value of Kw is 2.93 times 10 to the minus 15. That's because it's at 10 degrees C. Divided by the concentration of OH minus, which is 0.0262. That comes to 5.41 times 10 to the minus 8. Take the negative log of, sorry, it's not right. It doesn't come to that at all. Kw divided by that gives you, 1.18 times 10 to the minus 13. Take the negative log of that, you get 12.95 to 2 dp. That is the pH of the solution. And I think in the mark scheme, if you forgot that it was only, that it is, you get 2 moles of OH minus for every 1 mole of calcium hydroxide, you probably get 2 marks out, or 1 mark out of 3 or something. That is the right answer there. Right, so that's the end of the pH. Oh, no, it's not. Okay, it's not the end of the pH question because it carries on here. Right, so you've got it says your calcium hydroxide solution. And that's a saturated solution, so no more calcium hydroxide will dissolve. And the concentration is equal to, that. Now, you're going to do the same with magnesium hydroxide. So add that much magnesium hydroxide to water. Now, magnesium hydroxide, if you remember, is much less soluble than calcium hydroxide. The solubility increases as you go down group 2 with the hydroxide. So magnesium hydroxide is very insoluble. Barium hydroxide is fairly soluble. This is much less soluble. So the OH minus concentration here is going to be a lot less than like it was in the calcium hydroxide. It was double that, wasn't it? 0.262. It's going to be way less than that. So that means that the H plus concentration is going to be bigger. So that means the pH is going to be lower. So it would have a lower pH. It wouldn't be 12.95. In fact, it'd probably be about 8 or something like that, much, much lower. Okay, so that's the explanation bit. Right. So that's tying up your knowledge of group 2 with pH, calculating pH. Right, now we go into the mass spectroscopy. There's a mass spectroscopy question, time of flight. Right, it gives you the abundance of titanium isotopes in percentage is okay. All those percentages do add up to 100. We want the relative atomic mass. So the relative atomic mass, you add them all together. So you would do 46 multiplied by 9.1 over 100. To make life easier, just put them as decimals, 491. And then you plus 47 times 0.078 plus 48 times 0.746 and so on, blah, blah, blah. It's kind of a GCSE question, really. And give your answer to 2 decimal places, you get 47.8 is the AR. And again, it's always worth doing a common sense check on these things. Look, most of it is 48. All right, so it's going to be about 48. But you've got a fair amount of these 2 ones which are a bit lighter, so it's going to be below 48 rather than above, and it is just below 48. So that seems about right. Right, so they're going to, okay, time of flight. Write an equation, including state symbols, to show how an atom of titanium is ionized by electron impact. So you're going to have Ti gas plus an electron goes to Ti positive charge, and you've knocked an electron out, so that's 2e minus. And it's okay actually just to get rid of that electron on that side and just have one electron on this side. That's fine, but you do need the state symbols, and it's got to be gas. And the mz value, the one that would reach the detector first, that would be the lightest one. Why is that? Because they all got the same kinetic energy, half mv squared. So if m is smaller, v is going to be bigger, so it's going to get to the detector first. And this the lightest ion of titanium, or isotope, is going to be the 46, one that weighs 46. So it's going to be the one that's 46. Okay. Next bit, calculate the mass in kilograms of one one atom of 49 Ti. Now, the reason why they're asking you kilograms is because for this expression here, kinetic energy is equal to half mv squared. The mass has got to be in kilograms. If you want the kinetic energy in joules, it's one of the few occasions we use kilograms in chemistry. The mass has got to be in kilograms, and the velocity is in meters per second. Okay. Right, so let's do that. So the mass of a 49 Ti atom is going to be 49. 1 mole weighs 49 grams. Okay. So how much does, that's 1 mole. So 1 atom is going to weigh 49 over the number of atoms in a mole, the Avogadro number. That's going to give us the answer in grams. We want the answer in kilograms, so we've got to divide it by 1,000. So put that over 1,000, and the answer there is 8.137 times 10 to the minus 26 kilograms. Okay. Now, let's move on to the next bit. Right, now they actually give you a bit more information than you really need in this question here. So let's just have a look at it. It says it combines, basically it's combining the kinetic energy is equal to half mv squared. And we know that velocity is equal to distance of the tube over time. It combines those two, rearranges it to give us that equation. So they sort of help us out by giving us that. Right. Right. And D is the length of the flight tube. Mass M is the mass in kilograms of an ion. They tell us the kinetic energy here of an ion is that. We'll see we actually don't need that, but they tell us it. And they give us the time of flight of the 49 ion, 49 one, and we've got to find out the one of the 47. Right. So the way I would do that is this. We know in this expression here, the energy is the same, the mass is different, the time is going to be different, but the length of the tube in each case is the same, D is the same. Okay, now, so what you could do is you could work out the length of the tube D by putting in the mass of the 49 and the time of the 49, work out D, and then use it again, but put in the values for the 47. But there is a quicker way of doing it than that, a better way. Right, so what I'm going to do is, I don't like square roots in equations because it gets confusing. I'm going to square that to get rid of it. So I'm going to write down t squared is equal to d squared mass over 2e. Let's rearrange to get d squared. D squared is equal to, now let's do it for the 47, T47 time taken with the T47 squared multiplied by 2e over the mass of the 47. And we also know that d squared is equal to the time of flight for the 49 squared times 2e divided by the mass of the 49 isotope. Okay, now we know that we're going to substitute in the mass there. So the mass is, I'll just do it for this one, T47 squared multiplied by 2e. Now the mass of the 47 is equal to it's going to be 47 divided by the Avogadro constant and divided by 1,000. That will give you the mass in kilograms. Okay. Right. So, and then with the same for this one, for the green one, d squared is equal to T49 times 2e over, well, that weighs 49 over the Avogadro constant multiplied by 1,000. So I missed a 1 out there. So we can see the d squared is the same for each one. So I'm going to get rid of that and that. And we can see that that has got to be equal to that. Now we can cancel out a lot of stuff there. We can cancel out the 2e, so we don't need to know the energy. We can cancel out the Avogadro constant and the 1,000. That goes. So we just end up with that. Now we've got to work out the time of flight for the T47. So let's rearrange. So we get T47 squared is equal to the time of flight for the 49 squared multiplied by 47 over 49. So put the numbers into there. They give us the time of flight for the 49. That is 9.816 times 10 to the minus 7 squared. Multiplied by 47 divided by 49. That gives us an answer of 9.242 times 10 to the minus 13. Square root it to get t for the 47. That gives you 9.61 times 10 to the minus 7 seconds. Right, let's give it a quick common sense check. Look, it's about the same time as the 49, which seems about right, but is a little bit smaller, and it should be a bit smaller because it's a little bit faster because it's lighter. So that seems, and it is the right answer, and it seems like a good answer too. Okay, now let's do the last question. Well, that's this half of the paper, and do the next half of the paper in the next video. Right, so this is a thermodynamics question. We've got titanium 4 chloride can be made in that equation here. They give us the entropy values here, and they give us the delta H value. So what we've got to do, and we've got to find out delta G. Okay, so don't forget delta G, and you need to know that equation is delta H minus T delta S. Okay, so let's work out delta S. So what we do is we work out the entropy of the reactant. So delta S is equal to the sum of the entropies of the product, minus the sum of the entropy of the reactants. So we do, right, that's 253 for that there. We've got 2 moles of carbon dioxide, so it's 2 times 198. Add that lot together. So the delta S, the products, that comes to 649 joules, okay, per Kelvin per mole. And then for the reactants, do that in a different color here. We've got 2 times 223 for the chlorine. That's pretty high because it's a gas. Look at the carbon, it's really low. It's 5.7. It's graphite is the standard form. Diamond is even lower than that. It's a really low entropy because it's a highly ordered structure. And then titanium oxide, that's 50.2. Add all that up, you get that is 507.6. So that means the entropy change is equal to, and I'll put a sign in there, it's positive 141.4. So entropy is going up as you go from left to right. Okay, right. Now we've got to remember that is in joules per mole per Kelvin, and delta H and delta G we usually measure in kilojoules. So we need to convert this before we do anything to it. So that's equal to 0.141 kilojoules per mole per Kelvin. Right, put this into our delta G expression. All right, we need to work out what the absolute temperature is. So they tell us the temperature is equal to, what do we say, 989. So in kelvins, that's, we've got to add 273 to that. That is equal to 1,262 kelvins. So it's just a matter of putting those numbers into the equation to find out delta G. It's a pretty easy 60 marks for 6 marks. There's not that much to do there. Delta G. So delta H is minus 60 minus 1262 multiplied by 0.1414. That gives us minus 60 minus whatever that is. And the answer altogether is minus 238 kilojoules per mole. So delta G is negative, so therefore the reaction is feasible at that temperature. Okay, and in actual fact, that reaction will be feasible at all temperatures, won't it? Because, well, even if temperature gets higher, this thing gets even more negative, and so delta G will always be negative at any temperature. That was just a quick thing before we finish off. The reaction is feasible. Does that mean it will happen? Well, we don't know, because it doesn't tell us anything about the rate of reaction. It just tells us it's thermodynamically possible. The rate might actually be very slow. Anyway, that I'm going to leave that there, and we'll carry on with that's the end of question 5. We'll do question 6 in the next and the rest of the paper in the next video.